Hello viewers and welcome to another episode of Space Science with Python. Last time we had a small introduction into the ecliptic coordinate system using SpicyPy and Matplotlib. So we visualized the positions of Sun, of Mars, of Venus and our Moon for basically any time in a sky map. And the sky map, if you recall, was a geographic projection function from Matplotlib. So we had to play a little bit around to visualize our data. And at the end, we verified it also with Stellarium, and we were able to create a sky map for any date for these objects in Skyplot. And today, we will continue working on sky maps, but we will focus now on the equatorial coordinate system. Now let's recall the equatorial coordinate system with Stellarium. As you may remember from one of the previous sessions, the equatorial coordinate system is a coordinate system that if you have a telescope mounting that also has an equatorial mounting and a small engine, you can track the objects in the night sky in this equatorial coordinate system. So basically everything is running with, let's say, the rotation of the Earth. So let's go a little bit into the night. You see our camera is already aligning with some coordinates. And if we have now here the night sky, let's focus on a small star. Maybe take this one here. Then we can focus our camera, our telescope to the star, and then over the night when the Earth rotates and the night sky, so the night sky appears to be rotating above our heads, our telescope is tracking the star or nebula or whatsoever, and we can take long exposure recordings. And this is like let's say, the most common coordinate system for earthbound observations for amateurs and professionals alike. And today we will compute the position of the planets as last time, of Mars and Venus, as well as the Moon, and also the Sun in equatorial coordinates, and see how the plot deviates from our last time. Now for this, I already started VS Code and also my remote container. And we have basically the same setup as last time. So we have now a first cell where we compute the date time, a datetime UTC timestamp, and convert it to ephemeris times here in the very first cell, and importing some libraries. We have here again our pandas data frame where we add the ephemeris time, the UTC time. We have a dictionary with the Sun, the Moon, and Venus and Mars. We have some body colors later for our plots as last time, and we compute here in a similar style like last time the coordinates of the objects, but this time not in ecliptic J2000, but you see here a small difference in J2000. This is the equatorial coordinate system. And of course, I didn't call it this time like direction Sun with respect to the Earth ecliptic, but I picked up EQU like for equatorial. And then here in line 16 to 19, we are then computing the longitude and the latitude. And I know here in our case, it's not called longitude and latitude. It's actually called right ascension and declination. But yeah, let's stick with this longitude latitude annotation to not confuse too much. And then for Matplotlib, as you may also recall, we have to do some processing of the longitude values because the geographic projection as implemented in Matplotlib does not help us for our astronomical coordinate systems. So we had to play around a little bit. If you want to have a small deep dive into this equation here, I just recommend the video from last time. Now you could say, okay, wow, cool. So we can now simply plot everything and we are done. But I would like to show you the difference between the ecliptical and the equatorial coordinate system by plotting a particular line into our sky map. And this line is the ecliptic plane. So basically the equator in our ecliptic coordinate system must be somehow transformed into something else, an equatorial coordinate system. And I would like to show you how the ecliptic plane or line looks like in equatorial coordinates. And our objects like the Sun, Venus, Mars, and also the other planets should be more or less allocated along this line. So for this purpose, I would suggest we create a second data frame. And this data frame is a data frame that contains values of our ecliptic plane. Let's call it simply eclipse plane df. And here we add simply two columns. The one is the longitude and the other one is the latitude, or the coordinates of the ecliptic J2000. Longitude radians in radians, and there we say, okay, it's quite simple in ecliptic coordinates. It's basically from 0 degrees to 360 degrees, or 2 times pi. And yeah, let's do a Lin space, so equal distance of 100 steps between 0 and 260 degrees. So a small column, and the same thing applies also for the latitude, but the latitude is of course very easy. The latitude is basically pi half. Well, now you will say, wait a second, maybe you digested this this equation and said, hold on, it should be 0 degrees. It shouldn't be what is pi divided by 2? 90 degrees. That's quite confusing and strange. Well, this is again some kind of trick, let's say, how SPICE works. So 0 degrees is not like the, let's call it the equator of a sphere. It's more defined from 0 to 180 degrees, bottom top. So to reach the middle, we have to get 90 degrees. Otherwise, we would just have one of the poles, and this is not what we want. But again, this is something that you only know if you work with SPICE and all the tools over time. So it's the same thing a little bit like with matplotlib, right? You have certain values, but plotting requires some more engineering because the logic and the plotting is a little bit different. So this is what we need to do. Okay, so we can now convert this, because what do we want to have? We want to have the longitude and latitude of this ecliptic plane in right ascension and declination. And we used SPICE for this. Now, before we use SPICE, let's plot from time to time our data frame. I didn't run the cell yet. I didn't run anything at all. Highly professional. Now, there's a small error, or wait a second. There is a short error. Yeah, I totally forgot, of course, to put the log command here. So it should be allocated to the data frame. Yeah, and now should be working. Yeah, perfect. So this is our longitude and latitude values in ecliptic J2000. Now, if you want to use SPICE, there are different functions how we can convert coordinates and coordinate systems. And I would like to show you one method where we introduce today 2 new functions. So what is the logic? First, we are converting the coordinate system into rectangular coordinates. So we are converting them into x, y, z coordinates. Then we apply a transformation where we transform the vectors that are given in ecliptic J2000 to J2000, so to equatorial coordinates. And then we convert these vectors back into our longitude, latitude values, or right ascension, declination values. So first, let's convert it to some vectors. How do we do that? Well, of course, first we need to define a new column. and we call it ecliptic J2000, call it direction or so, equals to, let's see if this fits eclipse plane df. We apply a certain computation. We will see this in a moment. Lambda x, and we use a new function of SPICE. It's called sphere rec. So what it does, it converts coordinates into rectangular coordinates. So let's take a look at the documentation of SPICE. Sphere rec, spherical to rectangular coordinates, convert from spherical coordinates to rectangular coordinates. This is what we need, right? And we need three inputs. We need the distance from a point from the origin. In our case, it's the unit sphere, so we can say the radius is 1. You could also say 1,000 or 1,000,000. It doesn't really matter. And then we have to put the latitude or the co-latitude and the longitude values. So you see here the definition: angle of the point from the z-axis in radians, and then also the longitude. And since we are talking about spherical coordinates, we need, of course, this definition as here, because this is how also SPICE implemented it. It defines the 0 and 180 degrees at the poles, so the equator is at 90 degrees, so half a pi. Okay, this won't fit here completely, so let's make no, I don't want to make a comment. I want to make a line break. And then we say spicy pi. We say that r, the radius, is 1. This is okay. And then we say that colat is equal to the one column called ecliptic latitude radians. Yeah, this fits in the line perfect. And then we have also longitude, and the longitude is also the x value, but not the latitude, but the longitude. So just have to change this one here. And then, of course, we have to apply this along the axis 1. Thank you for the auto-completion again. Maybe not here in the function, but more here. Went through. There is still some mistake. R equals 1. Oh, I did a unexpected keyword argument long. Okay, let's take a look back. It is called long. That's weird. Maybe Spicy Pie renamed it in a way. Let's just make a small cell. Spicy Pie svrec. Huh, it's called lon, you see, LON here. Okay, so we have to remove the G. Now this should work. Ah, it works. Perfect. And now we have our our direction values. So these are unit vectors basically in ecliptic coordinates that are pointing at the ecliptic plane. Okay. Now we need to convert the vectors from ecliptic J2000 to J2000. Now, how do we do that? For this, SPICE has another nice function. It's called pxform. Let's have a look. Pxform says that it returns the matrix that transforms position vectors from one specified frame to another at a specified epoch. So this is what we need. We want to convert something from ecliptic J2000 to J2000 at a particular time. Now, ecliptic J2000 and J2000 are, let's say, steady state, so they are independent of time. But we have to provide a time, so we can just use the ephemeris time of today's session, let's say. And then we have to apply the matrix for the conversion. And how does it look like? Here it's how it looks like. If this is the matrix we get, the 3 times 3 matrix, and we can apply it to a vector xyz, and we get new xyz vectors that corresponds to our output frame. So we will see how this works in a moment. Now we want to convert ecliptic coordinates to equatorial coordinates, and this will be a matrix 3 times 3, and we need spicy pi dot px form. There's also another function called sx form, and this converts also the velocities. So then it's a 6 times 6 matrix. So you see, it's pretty nice what Spice provides. Now we want to convert from eclip J2000. We want to convert it. I have to make some adjustments with the auto completion. This is a little bit bothering. To J2000, and the date time, the ephemeris time, is what we already defined on top, date time ET. Ah, this works perfect. Before I show you the result, let's have a look. If we want to convert from ecliptic J2000 to ecliptic J2000, the resulting matrix should be a identity matrix. So on the diagonals you have ones and the rest is 0, because converting from one coordinate system to the identical coordinate system doesn't require any conversion, right? So let's see how the matrix looks like. And voila, we see what we have only on the diagonals ones and the rest is 0. So how does it look like if I have the J2000? Probably less trivial. Yeah, this is our result. Cool. So let's continue working on this one. We have now the transformation matrix, and now we can say, okay, I would like to convert the ecliptic plane df. Let's define it new. So let's say we want to have the so-called J2000 direction. Direction? Yeah. And this is where we apply eclip plane df, where we apply the metrics to all ecliptic J2000 entries. So let's say apply. And we see this exceeds the line limit a little bit. So let's make a break. Apply lambda x. And then we see eclip equal to matrix. And then we have to use the dot product on x. So this should result into direction values in J2000. Now let's make some execution, no errors, and let's have a look. We have a new column called J2000 direction, and these are our new results. Cool. Now we need to convert these direction values back to longitude and latitude values, respectively called right ascension and declination. And how do we do that? Well, we do it similar as we did it last time. I can just, first we can compute the longitude. So let me maybe copy paste it here. Longitude J2000 long rut equals to ecliptic plane df J2000 direction, and there we apply a spice function. This spice function will be again spicy pi rec rut. We already had this, I think, a week ago or so. And we're exceeding the line limit again, but don't worry, we'll just go back. And I think here, yeah, so this should work. The same again also applies for the latitude. Latitude is the second here. Okay, let's check. Yeah, this works. Now let's check it here. and we got the longitude, latitude values, and then you will see, wait a second, longitude value, this is quite a large value. For plotting, this will cause an issue. We have to again apply our logic that we defined last time for matplotlib. So we have to again make some data engineering for, I call it the J2000 longitude radians for plot. So otherwise we will not see anything. You can try it out without using this one here and see what happens. Yeah, the graph will be completely broken. So just try it out. Okay, so we can hear the long rut. Did I? No, I didn't copy the quotation marks. And then we apply. What do we want to apply? Yeah, lambda x, of course. And I think I had it here defined prior, right? Yeah, I just can copy paste it from the beginning. This is from last time. Again, if you want to have a deep dive, just take a look at my last video. Okay, I just also imported lambda, but not entirely lambda, only ambda. Yes. Hey, this is the caps lock. This should be fine. Red plot, longitude, yep, this looks fine. Let's check it out. No computation error, and we get a new column, the J2000 long red for plot. Now I don't want to redo all the plotting again. We can simply reuse the code from last time. So I just put it here in some, let's call it cache, where I can simply copy paste it here. It's basically the same code as last time. We're creating a figure, we're creating an ITOF projection with a title. We are iterating through the solar system dictionary and the body colors again. And then we are, of course, we have now different names now, equatorial coordinates. The only difference to last time is that we are also plotting the ecliptic plane as a blue line. And then we are also changing the ticks from minus 150 degrees to 150 degrees, changing it to radiance coordinate, to right ascension coordinates. So basically 10 hours, 8 hours, 2 hours, and so on. 0 hours is in the center, and then 22 hours down to 14 hours. So which means in our plot at the very end, we have 12 hours, respectively 180 degrees. And of course, the labels are also different. Now let's execute this code here. And we got an error. Yeah, J2000, the J is small, okay? This shouldn't bother us too much. We got a result. And now let's see how it looks like. We have the equatorial coordinate system now with our right ascension giving in hours and our declination in degrees. And as you can see, the ecliptic plane is not now a straight line anymore. It reminds us a little bit of a sinus function, right? And along the sinus function, you see also now the Sun, Mars, and also Venus. And if you recall, Venus is now currently a little bit below the ecliptic plane, so this looks quite nice. And we can verify this or take a look at Stellarium to see how Stellarium visualizes everything, right? So we can, here's 0 degrees, yeah, exactly. And we can, there's Venus, we have here the Sun, and we have, of course, different options to visualize this stuff. So we can, where was the markings, was it? What was it? Ecliptic plane? There it is. It's a thin red line, so this does not, it's not very, you can see it, I think, right? I think that should be fine. And maybe we can also change a little bit the, no, do we have also Mercator projection? Hammer ITOF is also here. Perfect. So we can also have the Hammer ITOF projection. Now we have to take care a little bit. Regarding 0 degrees is here, so this is the center. No, 0 degrees is here, of course. So we have to align it a little bit to center it. And now we see, we have here the Sun, we have Mars, Venus, and also Moon. So this shape reminds us of this shape here and also the positions, which looks nice. And let's take a look. Mars and Sun are at around 14 hours and declination is around minus 15 degrees. Now let's click simply on the Sun. 14 hours around, minus 14 degrees. Yeah, this looks nice. Same also for Mars. Mars is quite close to the Sun. Venus here is at around 17.5 hours and minus 30 degrees almost. And this, yeah, fits also here quite nicely. And the Moon is currently at 10 hours right ascension and 15 degrees, let's say, declination. So where's the Sun? The Sun is hiding here behind the text. What did I just say? 10 hours? Yeah, 10 hours. Yeah, looks nice. And 15 degrees declination. So cool. We did it. We converted successfully our ecliptic coordinates into right ascension declination. So now you're able to compute right ascension declination values and really give it an amateur or a professional astronomer and tell them, hey, this is my coordinates, so please do it. Now, we can also convert or compute other values. We can compute, for example, also the ecliptic plane. I told you, I think a week ago, that we have also the so-called galactical coordinate system, where the Milky Way is like the like the equator of our sky map. So we can also take a look at the ecliptic plane, the galactic plane. Not the grid. This would be extremely confusing. Where is the galactic equator? There it is. So take it as an exercise to compute maybe also the galactic plane here. You see it here. And this is the result that comes from the galactic coordinate system. So yeah, as a summary, what did we learn today? We learned how to convert from ecliptic coordinates to equatorial coordinates and plot them with matplotlib. So it's a little bit, sometimes a little bit confusing, but it works. We are now able to compute coordinates of different objects in equatorial coordinates, and you can literally give these values now or type them into your telescope mount or give it some amateur astronomer and do some observations. So you have all the tooling now you need to really do this on your own in Python, not only using planetarium software, but really simply in the shell or in your Jupyter notebook or wherever, or creating your own library if you like. So I hope you enjoyed it. I know it's a little bit tedious maybe, but think about it a little bit when you are, for example, checking some tutorials about machine learning. So most people would like to start immediately with deep learning. They want to see random forests and so on. But the basis or the fundament of machine learning, for example, is math, right? And statistics. So you have to learn a little bit statistics and mathematics first before you understand the algorithms of machine learning. And the same thing applies also in space science. You have to understand the basics of the coordinate system. You have to know what is an astronomical unit, what is right ascension declination, how can I compute it, before we start analyzing really interesting observational or in situ, so data out of space, so in data recorded by instruments in space. Before we have these science projects, we have to cover the basics first. Otherwise, these projects will be a little bit too confusing with all the terminology and so on. Anyway, I wish you happy coding. I wish you all the best. Take care and see you next time.